All right, so in this video, I'm going to talk about the largest application for AP Calculus. Well, one of the largest ones. There are a couple of others, obviously, but like area and volume and sequence and series for BC Calculus, parametrics and polars. But one of the largest categories for applications is motion, velocity, and other rates of change. It is said that Newton invented calculus in order to solve physics motion problems. So before I get started on some examples, graphically and analytically, I want to do some notes first on the calculus of motion. Okay, so let's talk about the calculus of motion. Well, first of all, there's a function that we typically call. Now, of course, my pen doesn't work. Position. Okay, and in calculus, oftentimes we use the function notation S of t for position. And we'll measure position in meters or feet or any other linearized unit like centimeters, inches, whatever unit of measure you can think of, okay? I'm going to create a position-like graph here, and I'm just going to make a parabola, if that's all right, because that's simple. So I'm going to use meters, and I'm going to use seconds here for my timeline. All right, so this is my position function, which is a function that states where I'm standing at time equals t. Okay, sometime t I'm standing at a position. So we'll put a t here. And I'm standing at this position, or my particle is in this position, or the ball I throw in the air is in this position at time t. All right. All right. Well, this position, my position, or the particle's position, has an instantaneous rate of change, which means it has a tangent line that has a slope, which is the instantaneous rate of change at this position. And if I think about what the slope is, and I'm just going to put a triangle here to indicate what the slope is. Slope is rise over run. Well, the units on the rise here are meters, and the units on the run are seconds. So the change in position over the change in time sounds an awful lot like velocity, and it is. So the instantaneous rate of change of position is velocity. And so velocity is the first derivative of position, and we'll write or denote it as v of t. And these units are typically meters per second, or feet per second, or inches per second, or gallons per minute, or whatever a rate of change would be over some unit in time for motion. All right, similarly, if I were to graph a velocity function, and if this is parabolic in motion, I'm going to have a linear derivative function, right? So this would be velocity. And I have positive slope, so I have positive y values, a zero slope, 0, and then negative y values. Okay, and my units on this velocity graph are going to be meters per second, and I'm going to have seconds on the x-axis. Now, obviously, this velocity graph has an instantaneous rate of change at some time t. We'll put t here. Which would be a tangent line here. And it's going to have a rise over a run. And the slope of this line is going to be meters per second. over seconds, which is going to be an acceleration because the rise units are meters per second, the run units are seconds. So the instantaneous rate of change of the velocity is going to be acceleration. Which would be the second derivative of position, the first derivative of velocity, and we usually denote that as a of t. And that's going to be in meters per second squared, or feet per second squared. And then acceleration has a rate of change. And I think we can follow the pattern now. And its instantaneous rate of change is a quantity we call jerk. And that's going to be the third derivative of position, which will be the second derivative of velocity. And that'll be then the first derivative of acceleration. And we'll denote that with a J for jerk. And the units on jerk are going to be meters per second cubed or feet per second cubed if you follow the pattern. Okay, now these three functions here are instantaneous rates of change. That means it's a rate of change at a moment in time. And those are derivatives because that's what a derivative is. Okay? So there's a relationship between the position, velocity, acceleration, and jerk when you're in motion, which is pretty cool. All right, now there's another rate of change that has to do with motion in calculus, and it's called the average rate of change. Now, the average rate of change, for example, if we want to find the average velocity, of a function between 2 points in time, well, that's just something we're really familiar with. That's going to be the change in position, delta S over delta T, which is the change in time. Now, delta is a bigger change in time than the derivative, which is a smaller change in time, infinitesimally small change in time. So delta S is nothing more than taking the position function and finding the slope of the secant line through 2 points. So it would be S of T2 minus S of T1 all over T2 minus T1. Okay, so that's the position at time 2 minus the position at time 1 all over the change in time, which is time 2 minus time 1. And if you think about the units here, the units would be, well, position, as we stated up here, was in meters over seconds. And you can see how now this quantity that we have talked about is a velocity because it's a meters per second. Well, this is not at a moment in time. This is the average velocity between 2 moments in time. Okay, now what's key here is that we notice that I'm finding a velocity, but nowhere in the calculation am I using the velocity function, which might appear to be a little strange, but I'm not using the velocity function, which is an instantaneous rate of change of position. When I'm finding average velocity, using the position function over time. So it's the net change in position over the change in time. Now, this quantity in the numerator here is called something specific in physics that you might recognize. And delta S, another fancy physics word for this is displacement. So the average velocity is the displacement, or delta S, over the change in time. All right. So similarly with velocity, there's an average acceleration. And that too is over an interval of time. And if average velocity is the change in position over the change in time, well, acceleration then is going to be the change in velocity over the change in time, which would equate to the velocity evaluated at time 2 minus the velocity evaluated at time 1, all over time 2 minus time 1. And if we think about the units on this calculation, well, that's a velocity, so the numerator would be meters per second. And the denominator here is going to be in time units, which will be seconds. And so we get meters per second squared, which is an acceleration unit. Okay, I want to stress again that acceleration, when you're calculating the average acceleration, uses the velocity function, not the instantaneous acceleration function. All right? Because the instantaneous is 1 point in time, the average is 2 points of time, and this is the slope of the secant line to the velocity function between 2 points. Then we can have average jerk. And that again is over 2 points in time. And that's going to be, you guessed it, the change in acceleration over the change in time, which is going to equal the acceleration evaluated at time 2 minus the acceleration evaluated at time 1, all over time 2 minus time 1. And if we think about the units, in the numerator, we're going to have meters per second squared over seconds, which gives us meters per second cubed, which are the units for jerk. Okay, so we have two different types of rates of change. We have the instantaneous rates of change that involve the derivatives and evaluated at 1 point, and the averages, which are evaluated over an interval of time, which are the slopes of the secant lines to the position and velocity and acceleration. All right, now I wanted to tie a little bit of this together with the pre-cal that you might have learned last year, or hopefully you learned last year. Okay, and so we're going to recall the motion, the projectile motion, or the free fall motion equations that we learned last year. And h of t, which would be the height of your ball or something you throw in the air, or you threw in the air. Oops, I didn't mean to hit the camera. That's kind of funny. Was equal to negative 16 t squared plus v original t plus h original. Right? So this would be negative 16 t squared plus v naught, or v original times time plus the original height. Now, knowing what we know about calculus, the calculus of motion, this is our position function, and I'm going to find the velocity and the acceleration here. Okay, now how do we do that? Well, the instantaneous rate of change, or the velocity, is the derivative of the position, because this is position. All right, so let's take the derivative. Well, you use the power rule here, and we could say that it's going to be negative 16 times 2, which is negative 32t, plus the derivative of v original times t, which would just be v original. And that would be the velocity function. Okay, and then I could find the acceleration by taking the derivative one more time, and this would be negative 32, which I hope is a number that's very familiar to you. This is the acceleration. Okay, this is the acceleration due to gravity in English units. Okay, so g, which is the acceleration due to gravity, Okay, English units. And of course, this is on Earth, right? Of course, we could be on another planet. It would be a different unit, obviously. That's going to be negative 32 feet per second squared. Okay. All right. And G in metric units is equal to negative 9.8 meters per second squared. Okay, so there's another set of equations here. This would be the English units. And let's do one for the metric units, okay? So h of t would equal negative 4.9 t squared plus v original times t plus h original. So the only thing that changes is the 16 turns into a negative 4.9. And the reason for that is obviously when I take the derivative, let's take the derivative to find the velocity function. It's going to be negative 4.9 times 2, which would be negative 9.8. And there it's arrived on the scene. You see the 9.8 times t plus v original. And then the acceleration is going to equal negative 9.8. And this is meters per second squared, and this is obviously feet per second squared. So you see the two gravitational constants there. Okay. Now, I like to point things out sometimes because sometimes physics and math, they're very related, but they write their formulas in a different way. And so I just wanted to tie one of the formulas here into physics. Okay, so we could write physics here. We could write this formula right here, the velocity formula, right? We could say the velocity is equal to negative 9.8 t plus v original, right? I could write this as v final, right? Because that's at some time. And then I could move this velocity original to the other side. And that's going to equal negative 9.8 times t. So some formula sheets have, in physics, have velocity final minus velocity original equals gt, right? So you might see it written in this format, but it is nothing more than the position function's derivative velocity rewritten in this format, which is pretty cool, I think. So they are all tied together, these two subjects, but sometimes it can be confusing that it might not look like they are, okay? So we have to talk about a couple of conventions when we talk about motion. And in calculus, we're going to talk about one-dimensional motion. Now, when I say one-dimensional motion, that means we're going to be moving in one plane. For example, we'll be walking along a line like this, left and right, or we'll be walking along a line or we'll be throwing something up in the air in a line, you know, like throwing it up and throwing it down in the same plane. All right, so some conventions in our language, okay? So we know that a body is at rest or stopped. That means not moving, right? We know that a body will be at rest or stopped when the velocity is equal to 0. That makes sense, I assume, to everybody, right? Because if you have 0 meters per second, you're certainly not going anywhere, okay? And this is the justification in calculus here. How do you know you're stopped? Your velocity is equal to 0. So that's your justification. All right. So a body will be moving right along that line I was talking about, or up if the velocity is greater than 0. That would be our justification if you want to know if something's moving up or right. Similarly, if our body is moving left or down, the velocity is going to be less than 0 or negative. Now, the next concept here is a little bit difficult for some students. It's not difficult once you understand it, but for some reason, folks don't like to necessarily remember. So I'm going to try to go into a little discussion to explain why. Okay, so knowing whether a particle is speeding up or a body is speeding up or slowing down. I said slowing up. That's not great, is it? Slowing down. That's kind of funny. Speeding up or slowing down. Of course, I'm writing in pen so you can see it better, and I can't erase it because I'm not on my smart board, but there we go, slowing down. I want you to consider for a moment, if you will, we're going to throw a ball in the air. So here's my ball, and I'm going to make it a baseball with, my nice little red stitches, because we are in baseball season, right? I'm going to throw the ball in the air. Now I'm going to show the motion in 2 dimensions here because just so we can write on it. But we're going to actually be throwing the ball up, and then it's going to come back down, like up in one plane and coming back down. But I'm going to show it spread out a little bit, right? So this is kind of the motion if you were looking at it from the side. Okay? So we're going to discuss what's happening. So when I throw the ball in the air from here, throwing it up, I'm giving it what? I'm giving it velocity in the up direction, which means the velocity here is positive, right? I'm trying to get a lighter color so you can see it. Okay, so this is velocity here is going to be greater than 0 because I gave it some initial velocity to throw it up in the air. And then at this moment right here at the top of the throw, something happens to the velocity. Well, you're right, it becomes 0. For a moment, the ball stops its motion upward and then goes down. So then what's happening to the velocity now on this side? Well, it's moving down. So the velocity on this side of the apex of the path is now negative. I think that makes sense to everybody, right? Because we're going up, and then we come to this part, and then we come down. Now, on this big turquoise planet of ours, we are under constant attack. Now, when I say attack, I don't mean attack, but something is constantly pulling down on us. And that's the acceleration due to gravity, right? It's constantly pulling down on us. So that's, since it's pulling down on us, it's moving down. So the accelerator, or not moving down, but the acceleration is going to be a negative quantity because it's pulling down on us. This acceleration due to gravity is always negative. Okay, so when I throw the ball up, I have positive velocity and negative acceleration. When I'm up here at the top, the velocity is 0, but acceleration due to gravity is constant, so it's still a negative quantity. So it's still negative. And then on this side, the acceleration is still negative because it's constantly negative. Okay, so if you think about it, I'm throwing the ball up with positive velocity and negative acceleration. And so what's happening is those two things are working against each other, and the ball is slowing down. And in your mind, when you throw a ball up in the air, it is slowing down until it gets to the top of its travel path. And then what happens? It starts speeding up back to the ground. Okay, so here we can say it's speeding up or slowing down. It's down, slowing down. Nice recovery, right? It's slowing down. Here it's speeding up. And the reason is the velocity and the acceleration are the same direction. They're working together. Here, the velocity and the acceleration are opposite signs and are working against each other. So the ball is slowing down on the way up. The velocity is 0 for a moment in time, and then starts coming down and it's speeding up towards the ground because the velocity and acceleration are the same signs. So in calculus, when you're justifying speeding up and slowing down, we know that a particle is speeding up when the velocity and the acceleration have the same signs. Right? Either they're both positive or they're both negative. We know we're slowing down when the velocity and the acceleration have opposite signs. All right, now what the big deal is here is that in calculus, oftentimes students, when they're asked the question, is my body or is my particle or is the ball speeding up or slowing down? They want to go directly and look at the acceleration only. Now, if you look at the acceleration only, you're not considering what direction your motion is. And the velocity is showing you the direction of motion because this is a direction, up, down, left, right. This is the direction of motion. And so if you are having an acceleration in the same direction as motion, let's speak, for example, you can be moving right and the acceleration is positive and you're speeding up in the right direction. You can also be moving left and have negative acceleration and you're going to have speeding up in the negative direction. So you have to compare the signs. I'm going to put this down in big letters. Must compare signs of acceleration or velocity and acceleration when determining speeding up or slowing down. Okay, and I'm emphasizing that. You might think I'm being silly when I emphasize that, but I don't want somebody on a test to if I ask something speeding up, they check the acceleration only and the acceleration is positive and they go, yeah, it has to be speeding up. It's accelerating. It's positive acceleration. But what if the body's moving left? Well, then it's slowing down. So just be careful of that, okay? All righty. Now we're going to move on to the packet. So you pull your packet out. Right here. Here's mine. And we're going to do several examples here on the calculus of motion. And what this packet says is straight line motion. And this straight line motion means we're in one dimension. So one-dimensional motion. Okay. Now, the question states, the graph below shows the position function of a particle moving along a horizontal coordinate axis. Graph the particle's velocity and speed. Okay, so position. We have the position, and it doesn't tell us any units, but this would be meters, maybe in seconds. So the slopes to this position function are going to be the velocity, right? Because the rise would be meters and the run would be seconds. And so the velocity function is going to be the slopes of this function, okay? So let's consider what the slopes are. Well, first of all, do I have any competing slope on this side? I'm starting at time equals 0, right? And at time equals 0, I don't have a slope on this side And so the slope coming into this point, I don't know. So we're going to assume that it's the same slope. But, the position function is not differentiable here in a couple of locations. And the reason it's not differentiable is that I have some corners going on here, right? You see this corner here? I have an abrupt change in slope there, and I have an abrupt change in slope here, and an abrupt change of slope here, and an abrupt change of slope here. So there are 1, 2, 3, 4 corners on this graph, this position graph, which means I'm not differentiable in the velocity graph, and I have to use an open circle at these locations, okay? So I'm going to do the velocity graph in green here. All right, so the slope from 0 to 1, 2, 3, 4, 5, 6, 7 is equal to 0. So I'm going to put a solid dot on 0 and then go 1, 2, 3, 4, 5, 6, 7. And it's going to have an open dot here. And I'm going to put a line here. So my slope is 0. The slope of the position graph is 0 from 0 to 7. Now, from 7, 8, 9, 7, 8, 9, 10, 11. From 7 to 11, the slope's going to be down 3 and to the right 2, it looks like. So it's negative 3 halves. Okay, so I'm going to have a point at negative 3 halves down here, negative 3 halves. Open circle in the middle here, and then 7, 8, 9, 10, 11. Here we go. Open dot here. Why do I have to have an open dot here? Because I have a corner here. It has to be open. And then we're going to go from 11 to 12, it looks like, and the slope looks like it's 1, 2, 3, 4, 5, 6, 1. So it's a positive 6. So I'm going to go up to 6. 1, 2, 3, 4, 5, 6. Here we go. Open dot. Open dot. All right. That's the slope from 11 to 12. And then from 12, 13, 14, 15, 16, 17, 18, 19. From 12 to 19, it looks like I'm back to 0 again. So 0. Right here, open dot. And it's got a 0 slope. And then the slope from 19 to 22 is 1. Okay, now I'm going to put a solid dot on this end. I have solid dots on my endpoints because I don't have a corner here. I just am going smoothly into the end, right? So I can have a derivative there at the end. Okay, so that's the velocity graph. Now, speed, by very definition, is the absolute value of velocity. Now let's talk about it. Last year when we were discussing vectors, vectors have both magnitude and direction. And velocity has direction because you can go right, left, up, down in our calculus conventions when we talked about that previously. But speed doesn't care about direction. It's just a scalar. Speed is a scalar, which means it just has magnitude. Magnitude only. And it doesn't care which direction you're going. It only cares about how fast you're going. Okay? And it's a positive quantity since it has no direction. Although you can have some negative scalars. But in this case, we're going to use it as a positive magnitude. Okay? Now, vectors can have some negative scalars. But in motion, speed is the absolute value of the velocity function. So it is going to be always positive because it's not taking into account your motion, it's the direction of your motion, it's how fast you're going. Like if you look at the speedometer, there's on your car, that's an instantaneous rate of change and it has no direction, right? I mean, it just gives you a number as how fast you're going. That's what speed is. All right, so on this velocity graph, there's only one location that I have to change, right? I have to change from 7 to 11 here because that's negative velocity, and I need to make it positive when I consider this the velocity graph or speed graph. So I'm going to take all the negative numbers and make them positive. but I'm still going to be 0, 1, 2, 3, 4, 5, 6, 7 to 7. And then I'm going to move this negative 3 halves up to a positive 3 halves for the speed graph. 7, 8, 9, 10, 11 to 11. Now that looks like a closed dot, but it's open. And then from 11 to 12, I'm still 6. And then from 12 to 19, I'm still 0. And then 1 to the end. Okay, so the only difference between the velocity and the speed graph is I take all the negative velocities and force them positive. All right, so let's answer some questions. The calculus questions, all right? So the first question says, when is the particle moving to the left? Well, I have to look at the velocity graph and determine when the velocity is negative, because that's how I know a body is moving left or right. Okay, so in this case, the particle is moving to the left from 7 to 11. Now I'm using open intervals here because I'm not differentiable there on the ends. And how did we know that using calculus? Well, we knew that since, and that's the symbol for since, or you can use the words, v of t was less than 0, and that's your justification. All right, the next question says, when is the particle moving to the right? Well, a particle moves to the right when the velocity is positive. Well, I have two locations on the velocity graph where the velocity is positive, so I can say it's moving to the right from 11 to 12 and from 19 to 22. Now, you can put a closed or a bracket here or an open bracket here because we don't know what's going on to the right of this. So AP folks will accept either a bracket or an open parentheses here. But how did we know our particle was moving to the right? Well, we knew that since the velocity was greater than 0, and that's our justification. The next question says, when is the particle standing still? Well, the particle is standing still when its velocity is 0, and so from 0 to 7, and again, we can use a bracket here if we like, or leave it open, 0 to 7, and that looks like it's from 12 to 19. Since the velocity is equal to 0. Again, that's our justification. And then the last question says, when is the particle moving the fastest? Now, fastest implies speed. So if we look at the speed graph right now, we can see that it's moving the fastest between 11 and 12. And our justification here is just going to be since speed graph has a maximum. Okay. Now, in future chapters, we're going to have a better explanation as to when that's a maximum or a minimum. Okay. But that's pretty simple. So in order to graph the position or the velocity function given the position, what do? You take the slopes of the position function and graph them. And then if I want the speed graph from the velocity graph, all you do is you take the negative velocity values and force them positive. And then you can answer some questions here, okay? All right. Now, the graph below shows the velocity of a particle moving along the axis, and we're going to graph the acceleration. Now, acceleration is the derivative or the instantaneous rate of change of velocity. So, like position and velocity, between velocity and acceleration, I'm going to just graph the slopes on this graph, okay? So I have to figure out what the slope is here. So it looks like we're going 1, 2, 3. Okay, let me see the dots here. 1, 2, 3, 4, 5, 6. 6 and over 2. So it looks like it could be a negative 3. Let's try again. 1, 2, 3 over. No, well, let's see. 1, 2. well, all right, this is the best way to do it. I'm going over 4. 1, 2, 3, 4. That's clearly 4. And then it looks like I'm going down 6. 2, 3, 4, 5, 6, 7. That's 7. So it's 13 over 4. So negative 13 over 4. What does that equate to? If I'm thinking of a decimal, right? 13 divided by 4 is about 3 and a quarter. 3 and a quarter. So it's a negative slope, isn't it? So negative 3 and a quarter from 1, 2, 3 to 4. So negative 1, 2, 3 and a quarter. So right about here. So I'm going to put a solid dot here, and then 1, 2, 3, 4. Put an open dot here. Why am I putting an open dot here? Well, because that's a corner, and we can't differentiate at a corner. Okay. Now the slope here looks like it's. Let's see. We're going to go down 1, 2, 3, 4, and over 1, 2, 3, 4. So it looks like the slope is 1. Now I'm just approximating, looking at the graph, my best guess here. So that's 4, 4, 5, 6, 7, 8. So we're going to go from 4 to 8. 4, 5, 6, 7, 8. A graph, slope of 1. And then this is an open dot, even though it doesn't look like it. Because my pen is pretty thick here. So then we have a 0 slope from 8, which is 8, 9, 10. 8, 9, 10. Oh my gosh, my eyes are having trouble. 8, 9, 10, 11, 12, 13, 14. So to 14, I have a 0 slope. So this is open. 8, 9, 10, 11, 12, 13, 14. Do these dots line up in here? Not quite, do they? 8, 9, 10, 11, 12, 13, 14. So 14. I'm just going to be consistent here. I'm sorry they're not the same separation here. All right, and then what kind of slope do I have after that? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 over 1, 2, 3. That's a 3 slope, and it's positive. So 1, 2, 3, open dot, and then we're going to go from. We said this was 8, 9, 10, 11, 12, 13, 14. So we're going to say 14 here. I'm going to put these down for reference. 8, 4, right? And so that's going to be 14, 15, 16, 17. And then that's going to be from 14 to 17. 14, 15, 16, 17. I have a 3 slope. So I'm at 3 here. And then after that, from 17, 18, 19, 20, 20, 17, 18, 19, 20, 21, 22. This is 22 still. My slope's going to be 1, 2, 3, 4, 5, 6 over 1, 2, 3. So that's a slope of negative 2, it looks like. Now this one has one more blurb on it, so this is 22 here. Yeah, all right. Well, so these are estimates on the slopes, okay, because it's hard for me to see. So let's make right, I'm estimating the slopes because these numbers aren't necessarily clear, and I feel bad they're not clear. But as long as you're approximating and showing what numbers you're using, that'll be fine when we're doing this, okay? All right, so let's answer some questions based on the graph we came up with on acceleration here. When does the particle reverse direction? Well, a particle is going to change direction, and I really should put on this chart here. How do we know something is changing direction? I didn't even address that, right? How do we know something is turning around and going the other direction? Well, velocity shows motion, right? So if I'm moving right and then I'm moving left, what happened to the velocity? It changes signs, right? So you know you're changing direction when the velocity changes signs, right? V of t either goes from greater than 0 to less than 0, or V of t goes from less than 0 to greater than 0. All right, so how do I know when the particle reverses direction, changes direction? I look at the velocity graph. It goes from positive to negative here, and it goes from positive to negative here, and positive to negative here. So I know that that looks like it's t equals 2. So we're going to say at t equals 2, at t equals, goodness gracious, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. At 15, and then if that's 22, that's going to be 20. Since V of t changes signs. Okay. Now, you could go into detail at each location as to when going from positive to negative and negative to positive and positive to negative. But for this discussion, I'm not going to do that right now. So when is the particle moving at a constant speed? That means its rate of change is not changing, right? So I would say it's going at a constant speed right here from 8 to 14. Right? Because is that the magnitude of this change here? Changing? No, it isn't. Okay. And this would be since V of t is constant over that interval. When is the particle moving at its greatest speed? That means when is it moving the fastest? Well, now remember, speed is the magnitude of velocity, right? So I am going to put a speed graph on here. So we're going to put speed in yellow here. I don't know if you can see that. Maybe I should put it a different color. We'll make it a little bit darker yellow. So can you see that? So we're going to, speed is the magnitude of velocity, right? So how do I draw the speed graph given this graph? Well, I'm going to take all the y values here that are negative and force them positive, okay? So we're going to go all the way to the top up here. This is 1, 2, 3, 4, 5, 6, 7 down. 1, 2, 3, 4, 5, 6, 7. So it's going to go all the way up to the top here. So it's going to go from here to here, and then it's going to go to 3. So 1, 2, 3. So it's going to go to here, right? Because I'm just taking these y values and flipping them up. And then we're going to go straight across to here. And then I'm going to go back down to here. And then this stays the same because it's already positive. And then we're going to take this and go 1, 2, 3, 4, up, 1, 2, 3, 4, up. And so the speed graph is this one, right? Because that's the absolute value of the velocity graph in black. Okay, so it's the greatest where? At t equals 1, 2, 3, 4. At t equals 4. Since it's the max, since speed is a maximum on the graph, on the absolute value of velocity graph. Okay? So those dots were a bit challenging for my older eyes, but we got through it. All right, so let's do another one. A searchlight is shining along a straight wall of a prison. A graph of the velocity of the light at 3-second intervals of time is shown in the graph, as long as as well as a table of values. Okay. Now the first question is, so this is a velocity graph, because this is feet per second. I know we can't see that, but that's feet per second, and this is in seconds. Okay. And then the question is, at what interval of time is the acceleration of the searchlight positive, right? Now, this is the velocity graph. So what is the relationship between velocity and acceleration? Well, acceleration are going to be the slopes of the tangent lines to the velocity. And they want to know when this is going to be positive. Okay, so the slopes of the tangent lines to this graph here are what? They're positive here, aren't they? They're positive until maybe here. Would you agree that the slopes are probably positive till about here, which looks like it's at 12. So we'll say from 0 to 12, right? And we'll say from, this is 15, this is 18, from 18 to 21, because then the slopes become positive here. Make this 18 so I can see it better. All right, and then from, that looks like 24 to 30. Now, how do we know that? Well, first of all, we know that velocity is increasing. And we can say positive slopes. Which means acceleration is greater than 0, because the acceleration are the slopes to this velocity graph, all right? Letter B, find the average acceleration of the searchlight over the interval 9 to 27. So we have to recall our average acceleration formula is, right, over, my interval is 9 to 27, is going to be the change in velocity over the change in time. Remember, we don't touch the velocity function or acceleration function, we touch the velocity. So we want v of 27 minus v of 9 all over 27 minus 9. Okay, so what is v of 27? Well, they tell us up here at 0, minus v of 9, which is 2, over 27 minus 9, which is 18. And so it's negative 2 over 18, which is negative 1/9 meters per second squared. All right, and that makes sense because it's velocity, which is meters per second over seconds. Part C, given an approximation for the acceleration at t equals 15. Now, acceleration is the slope at 15, right? So I want to say a of 15 is approximately, well, I don't have a function to take the derivative of to plug the 15 in, so I have to approximate. So I'm going to approximate using some points around 15. Well, what are the points around 15? Well, the points around 15 are 12 and 18. So I'm going to approximate the acceleration by using v of 18 minus v of 12, because that's around 15 over 18 minus 12. So the velocity at 18 is, what does that say? Negative 7 minus the velocity at 12, which is 4, all over 18 minus 12 is 6. So this is going to turn out to be negative 11 over 6. And so this is an acceleration meters per second squared, because it's the change in velocity over change in time. And this is an approximation, right? Because I'm using the secant line instead of the derivative to find it, and I'm just approximating it at 15. And if I go to my graph, does it look reasonable that that looks like a negative slope there? Yeah. All right, D. For what value of t is the searchlight speeding up the wall? Okay, so remember, speeding up, I have to compare the acceleration values and the velocity values, okay? So I need to know when the velocity is positive and the acceleration is positive. That means I need to know when the y values on the velocity graph are positive and the slopes are positive. And it looks like that happens between here and here and here and here, right? Because it's both y values and both positive slopes. Okay, so that's going to be 0, 3, is that, say, 6? Yep. So I'm going to say from 6 to 12 and what was that? 27 to 30. Since v of t is greater than 0, right? The y values are positive, and a of t is greater than 0, which means I have positive slopes to the velocity graph. All right, where else would that happen? It's going to happen when I have negative velocity values and negative slopes. So I would have negative values down here in the velocity. I have negative slopes from 15, it looks like. Oops. 15 to 18. And 21 to 24. Since v of t is less than 0 and a of t is less than 0. Okay, the velocity values are negative and the slopes are negative. Okay, all right, that's a good one. Moving right along. All right, I'm going to do one from the 1969 exam. This is the 1969 AP exam, and it was on the AB test, and it was on the BC test. Sometimes they share questions. Well, they share 3 of the 6 free response questions, okay? So let's work this one, okay? It says a particle moves along the x-axis in such a way that its position at time t is given by x equals 3t to the 4th minus 16t cubed plus 24t squared for negative 5 to 5 interval, okay? Now, I like to make a mental note that my time zone here is negative 5 to 5. So I don't give any answers that are outside of that zone, okay? All right, so here we go. Determine the velocity and the acceleration of the particle at time t. Okay, well, that's easy enough. I just take the derivative of this. So using the power rule, the derivative of this would be velocity, which is equal to 12t to the 3rd minus 48t squared plus 48t. Acceleration is going to be 36t squared minus 96t plus 48. And then I have 2 points out of the 9, which is really nice. Part B. For what values of t is the particle at rest? Well, how do we know something's at rest? Well, we know it's at rest when the velocity is equal to 0. So I'm going to set this velocity function equal to 0, which would be 12t cubed minus 48t squared plus 48t equals 0. And I'm going to factor this. So I'm going to factor out a 12t, and I'm left with t squared minus 4t plus 4 equals 0. And 12t, and this will be t, and t equals 0. And then I've got a 2 here and a 2 here, and this is a minus and a minus. And so this is 12t times t minus 2 quantity squared. Okay, so I know that that's 0 at t equals 0 and 2. So that's part B. Part C says, for what values does the particle change direction? Okay, for that, I'm going to need a velocity sign chart. So I know when the velocity is equal to 0. And I know that I'm living between -5 and 5 in time. And my velocity is 0 and at 2. And what shape is the velocity graph? Well, the velocity graph is a cubic function. And it looks like it has a 0 at 0 that's got a multiplicity of 1, a multiplicity of 2 on the 2, so it's going to have n behavior, like this. And I'm going to pass through 0 and bounce at 2. And so my sign chart's going to be negative y values, positive y values, and negative, or positive again. Okay, now what I am jazzed about, what I really like about sign charts, is that the velocity, remember, describes how your body is moving, your particle is moving. So I have a negative y value here, so I know I'm moving left, I'm moving right, and then I'm moving right, because these y values are positive. So I know that the particle at -5 starts out moving left, and then at time equals 0, it moves. So it's moving left, and then at time equals 0, it turns around, moves right, pauses for a moment, and then continues to go right. Okay, so my answer for part C is going to be the particle changes directions at t equals 0, since, how did we know? V of t changes signs. And sometimes I like to state that V of t was less than 0, and then it went to V of t greater than 0, right? I like to show the sign change. And this is an arrow. All right, so we know that the particle changes directions at t equals 0. Now I'm going to make a comment here. How did we know that the particle didn't change directions at 2? Well, we knew the particle didn't change directions at 2 because the signs didn't change, right? So the particle does not change directions at t equals 2, since V of t did not change signs. It went from going positive, paused for a moment, right, and then now it's still positive. So it went from positive to positive. All right, now part D says, what is the velocity when the acceleration is first 0? Okay, so I need to know when the acceleration is equal to 0. Well, the acceleration function I've got shown right here, that's 36 t squared minus 96t plus 48. And I'm setting that equal to 0. I can factor out a 12, and I'm getting t squared minus, 3t squared, right? Because when I factor out a 12, I'm still left with a 3. So 3t squared minus 8t plus 4 equals 0. And back in 1969, these things either factored or we had to do the quadratic formula. But I did this ahead of time, and I know that this factors. So it's 3t and t, and it's 2 and a 2, and they're both negative. So and the inner product is -2, the outer product is -6, so it does add up to -8t, okay? And then I know that t is either 2/3 or 2. And the question is asking us for what is the velocity when the acceleration is first 0? Well, it's going to be first 0 at 2/3. So I know the velocity is equal to 12t times t minus 2 quantity squared. And then I need v of 2/3, which is equal to 12 times 2/3 times 2/3 minus 2 quantity squared. And this is 24/3, which is 8. And then this is 2/3 minus 6/3, which is negative 4/3 squared, which will be 16/9, which is equal to 128/9. And they didn't give us units back in 1969 on this one, okay? Now, one question they didn't ask that I do like to do a review of really quickly, to get a taller view of what we're doing here. I like to find out when this particle is speeding up and slowing down, because that's something that they ask a lot nowadays. And I just want to make sure that we understand how to do that. All right. And so in order to do that, I need an acceleration sign chart. Okay. I have the acceleration function, right, which is a quadratic that opens up, right, and has 2 zeros at 2/3 and 2. So I'm going to do an acceleration sign chart here underneath the velocity one. And I'm going to make it from -5 to 5 again, just like the velocity one. And I have zeros instead at 2/3 and 2. And we said that the acceleration graph is a quadratic, so I'm going to superpose my quadratic, right? And if I'm going to do a sign chart there, the y values are positive, negative, and positive. Okay, and if I want to know when I am speeding up and slowing down, okay, so I'm making my own part E here, so I'm going to put E up here so we can see it. Speeding up. That means the signs are the same for acceleration and velocity. Okay, so I know they're opposite signs here from -5 until 0. Do you see how they're the opposite signs? And then what happens at 0? For a short period of time between 0 and 2/3, they're the same sign. So from 0 to 2/3, they're both positive, right? Because it's positive up here and positive down here. And then at 2/3, the acceleration goes negative while the velocity is positive. Okay? So they're opposite signs here, but then they become the same signs at 2, so from 2 to 5. And you can have a closed bracket here, but I'm just going to use open. It doesn't matter. The AP people will accept either. Okay? And I'm just going to write them down, then I'm going to justify them. So slowing down. So what are the intervals we're slowing down? Well, clearly we're slowing down from -5 because they're the opposite signs until I get to 0. Okay, and they're slowing down again from, it looks like 2/3 to 2 because they have opposite signs. Okay, so what's my justification? V of t and A of t have the same signs for speeding up. And here, V of t and A of t have opposite signs. Okay, so when I'm looking to see if a particle is speeding up or slowing down, I'm comparing the sign charts to see where they have the same signs or the opposite signs. Okay, so that's an important thing that I wanted to at least touch on in these notes. Okay, 1975, here we go. We're going through time. A particle moves along the x-axis in such a way that its position at time t for t greater than or equal to 0, there's my little notion here that time is greater than or equal to 0, is given by 1/3 t cubed minus 3t squared plus 8t. So it says, show at time t equals 0, the particle is moving to the right. How do we know something's moving to the right? Well, the velocity is positive. So for part A, I need to find v of t. So let's find v of t. That's going to be the derivative using the power rule. So it'll be t squared minus 6t plus 8. And I want the velocity at 0. Well, that wipes everything out except the 8. And since this is greater than 0, particle is moving to the right. At t equals 0, since v of t is greater than 0. All right, part B states, find all values of t for which the particle is moving to the left. Okay, well that's going to require me to do a sign chart. So let's find out when we have some zeros here. This is going to be t, and then -2 and -4, right? Because the inner product is -2t and the outer product is -4t. When you add those, you get 6. And when you multiply those, you get 8. So it works out. So that's at t equals 2 and 4. And I'm going to put my velocity sign chart over here. And we're going to start at 0. And then we go on to infinity because that was my limitation up here for time. And I'm going to put a 2 and a 0 and a 4 and a 0. And then I have to consider what the graph looks like of my velocity function. And that's clearly a parabola. Superimposing that, I get that, and then I can do my sign chart and say, well, the y values are positive here, negative here, and positive here. And I want to know the values for when the particle is moving to the left. And looking at my sign chart, I can say, well, I was moving right, left, right, which I love this for this reason. Okay, I can say particle is moving left for what intervals? Well, that's going to be from 2 to 4, since v of t is less than 0. Okay, I am not using closed brackets here because moving left means the velocity is negative. Not when the velocity is 0, I'm not moving at all. So I'm not making this inclusive here. All right, part C. What is the position of the particle at time t equals 3? Okay, so the position function they gave us was x equals 1/3 t cubed minus 3t squared plus 8t. So I want the position at 3. Okay, which means this is going to be 1/3 times 27 minus 3 times 9 plus 8 times 3. Okay, so what do we get? We get 1/3 of 27 is 9 minus 27 plus 24. Right, that's 9, that's 27, and that's certainly 24. Okay, and so when I subtract these two first, I get what? -3 plus 9 is 6. So I get x of 3 is 6. Okay, well that's easy enough. And then it says, when t equals 3, what is the total distance of the particle? What is the total distance the particle has traveled? Well, oh wow, so this is a little bit complicated. So I have to know the distance that it went from 0 to 2, right? I need its displacement from 0 to, or its position from 0 to 2. So part D, because it changed directions at 3, didn't it? I mean at 2. So x of 2 minus x of 0 is going to be the position, or how far it went from 2 to 0. So x of 2, let's use my calculator here because I'm going to do this. I know this video is getting a little long and I want to make it faster. So if I know that, I'm going to put my function in here. I'm going to say 1 divided by 3 x to the third minus 3 x to the second plus 8 times x. Now I'm using x because I'm doing a function of x here. I'm going to go back to the home screen and I'm going to say, because I put my position function in y1. Do you notice that that's y1? Okay, so I'm going to go home and I'm going to say I want y1 of 2. And we get what? Does that say 20 over 3? 20 over 3. Minus the position at 0 is easy enough, right? Because that's just going to be 0 when I plug in 0. So I moved 20 over 3, right? I moved right this far. Now I have to figure out how far I moved left. Well, I moved left from 2 to 3, okay? So when I go x of 3 minus x of 2, so I'm going to figure out what y1 of 3 is. Well, we already figured that out, right? That was 6. We knew that. So this is going to be 6 minus 20 over 3. And this is going to be 18 over 3, right, if I do the fraction, minus 20 over 3, which is negative 2 over 3. So I moved that far left. So what's the total distance traveled? Well, I'm going to add the absolute value of this to this, right? That's going to equal 20 over 3 plus 2 over 3, because that's how far. So I moved this right and I moved this left, and then I totally walked or traveled, the particle did 22 over 3. Okay, so that's how you would figure that out. All right, let's roll the clock one more time to 1983. We're doing particle motion over the decades. So hopefully you're starting to see a pattern to these things, okay? All right. The particle moves along the x-axis, so its position is given by t cubed minus 6t squared plus 9t plus 11. What is the velocity at t equals 0? Well, I need to find the velocity function first, which is the derivative of the position using the power rule, which would be 3t squared minus 12t plus 9. And I want v of 0, which is going to just equal 9. All right, that's part A. Part B, during what time intervals is the particle moving to the left? All right, well, I'm going to set the velocity equal to 0, and I'm going to factor a 3 out, and I get t minus 12, t squared minus, oops, helps if I factor better, 4t plus 3. Now, please notice it doesn't give me any time restrictions on this one. Okay, so let's see if I factor that right. Yeah, I feel good about that. All right, now we're going to set this equal to 0 and factor this, and we get t, 3, and 1, and they're both negative, right? Because the inner product 1t and the outer product are both negative. So negative 1 minus 3 is negative 4, and it works. So t is equal to 1 and 3, and now I'm going to do my velocity sign chart. I should label it first. There it is. And it's going to be 1 and 3, and I have zeros there. And I'm going to superimpose the shape of my velocity curve on this graph, which is a quadratic, opening up. And if I do the signs, we get plus, minus, plus. And so thus we know the particle is moving right, left, right. I feel like I'm in the military. Right, left, right. And I want to know when the particle is moving to the left. So we can say particle is moving left from 1 to 3. And I didn't include 1 and 3 because it's not moving at all at 1 and 3. Since v of t is less than 0. My v looks a little suspect there. Okay, now part C. What is the total distance traveled by the particle from 0 to 2? So I have to do that same thing. I know the particle changes directions, right? At 1. So I have to do, I'm moving right. So we're moving right from 0 to 1. And we're moving left from 1 to 2. So I got to find the distance I traveled right, which is going to be the displacement here. So this is going to be x of 1 minus x of 0. So let's figure out what that is. X of 1, if I plug 1 in the position function, we're going to get 1 minus 6, which is negative 5. Negative 5 plus 9 is 4. 4 plus 11 is 15. Minus 11, which is 4. Let's see if I did that right. 1 minus 6 is negative 5. Negative 5 plus 9 is 4. I feel good about that. Okay, so we 4 units to the right. Now, from the left, we're going to go x of 2 minus x of 1. Now, I know this is going to be a negative number, but that's okay because I'm moving left. So x of 2 is going to be, I'm going to have to do some work for that. Okay, x of 2 is going to be 8 minus 6 times 4 plus 18 plus 11 minus x of 1, which I already calculated, which is 15, which is nice. That saves me some time. Okay, so this is going to be equal to, well, 8 and 11 is 19. So it's going to be 19 plus 18 minus 24. And 24 minus 18 is negative 6. So this is going to be 13. 13 minus 15 is negative 2 from this, right? So I think that's right. So let's check our answer. And I'm suggesting that the total distance traveled between 0 and 2 is going to be equal to 4 plus 2, because this is how far I moved right and this is how far I moved left, and that will be 6. So let's make sure we're right, though, just before I terminate this video and have a wrong answer. Oops, I'm sorry, wrong calculator. Here we go. I'm going to go to F18, clear this out, clear. And then go to y equals and put in my position function. And I'm just going to put it in the second one here just to be x to the third minus 6x squared plus 9x plus 11. And notice that I'm putting this in y2. Okay? And what am I doing? I'm putting my position function in there. X cubed minus 6x squared plus 9x plus 11. Okay, so I'm going to go home. And then instead of y1, I'm going to go y2 of 1, which is 15, right? Which I'm very happy about. Okay, and I'm going to do this all at once. y2 of 1 minus y2 of 0, which is 4, right? So I did do my math right. Okay, and now I'm going to find out what y2 of 2 is. Yay, it's 13. I can add and subtract in public, but that's only for today. So we're going to go y2 of 2, minus y2 of 1. And we got negative 2. And so when you add those two together, you do get 6 units total distance traveled. All right. Phew. All right. So that's my straight talk on my one-dimensional calculus of motion. you know, velocity and other rates of change on horizontal and vertical lines. You guys have a great day.